Okay, for today's lesson, we're going to talk about 9.3 similar right triangles. And your essential question is, how are altitudes and geometric means of right triangles related? So we've talked about altitudes before. Altitude's basically like the height that you draw in a right triangle, in any triangle. So it's drawn from a vertex and it's perpendicular to the base of the other side. So if you think about, I'll just draw some random triangle here. Basically, your altitude, you draw it from a vertex down to the opposite side, and it's perpendicular. It's not a median, so it doesn't necessarily always divide the base into two. If it's an isosceles triangle, then it would do that, and you would form two congruent right triangles. That's not always the case, though, but that's just a good reminder for altitudes, always drawn from a vertex to the opposite side perpendicular. Okay, so let's talk about the right triangle similarity theorem. Oh, and before I get started, you're going to need a few colors for these notes, so I've got 3 different colors. And you can use pens, pencils, crayons, whatever you want to do. Alright, so I'm going to try and keep my notes pretty small because I'm going to end up drawing 4 different triangles in the space. So if the altitude is drawn to the hypotenuse of a right triangle, then 3 similar triangles are formed. Okay, so I'm going to start with my first triangle. I'll do it over here. So it's going to be a right triangle, and I'm going to let the hypotenuse be a horizontal line. Just pretend like that's a perfect right triangle. So I would take the vertex, that's the 90-degree angle, and I would draw my altitude down to the hypotenuse. And we know it's an altitude because it's going to form a right angle there. So you can see that I'm going to end up with 3 right triangles, right? So I have the first one. I also have this one on the right-hand side. And then I have another one over here on the left-hand side. This is also going to be a right angle. So you have the full one, and then you have a second one and a third one. Okay, so what I'm going to do now is I'm going to take each one of these triangles and I'm going to redraw them in the exact same position. So all corresponding parts will be in the same spot. So for example, I'm going to think about this right angle, and I'm going to put the right angle in the same exact spot for every single triangle. So I'll do that on the bottom left-hand corner of the triangle. Okay, so why don't I start with my pink one? Let's see. So I'm going to start with the big triangle. I'll make that my pink one. Okay, so I'm going to go ahead and draw now. Just rearranging it, rotating it really, so that the right angle is going to be in the bottom left-hand corner. And how about I give it the vertices some names? So how about we go with, this will be A, B, and C. So now my right angle is here, so that's my C. And basically what I've done is I've rotated it. Would that be right? Actually, I probably rotated it and flipped it because I'm going to put A up here and B over here. Okay, I'm going to make that the same exact color just so that I'm color coordinating everything. Alright, so this is A over here, this is A here, and then this is B here, And I'll go ahead and put B there. Now, when I do the rest of these, so triangle 2 and triangle 3, it's going to be really important that, the right angle goes here, the angle that's congruent with angle A goes at the top, and the angle that's congruent with angle B goes down here at the bottom, so that corresponding angles are in corresponding positions. Now, they won't always be called, sometimes they'll be called different things. For example, now we're going to have a right angle that's actually here. We'll call that D. So let's do triangle 2. I'll make that one a little bit taller. Okay, so now I'm doing triangle 2. So how about I make that one yellow? Oops, and I'll do this one too. Okay, so now my right angle is no longer C. It's actually D, right? And if you think about taking this and rotating it so that A corresponds with A, so this will also be angle A. Now the question is, well, what's that angle? Right? So you got to think about rotating this, and basically now angle C is down here. Okay, and then we're going to do the last one, which again, I'm going to keep that right angle in the bottom left corner. And now that right angle is actually D as well. This is triangle 3. And let's make it a different color. How about green? But now what's down here? Well, the angle that's going to be right here is going to be angle B. I didn't really even have to transform this one at all, right? There was no transformation done on it at all. No rotation, no reflection. Well, I guess I'm translating it just over here. Okay, so there's a B, and then C would be up here, right, because it corresponds with that. B is going to be congruent with that B. So now we have 3 similar triangles. So I could write a similarity statement, such as, now that I've got them all in the exact same order, this is going to be pretty easy. I'll start, for me, I'm going to start at the top and then work my way counterclockwise. So I could say that triangle ACB is similar to triangle ADC, and that's similar. Oops, I didn't put a triangle symbol. And that's similar to triangle CDB. So by putting them all with corresponding parts in the same position, I'm able to write my similarity statement really easily. And I totally messed that up. It's CDB, not CBB. There we go. Okay, so the right triangle similarity theorem really helps you realize that if you've drawn an altitude that touches the hypotenuse, which means that that altitude is going to start at the right angle of the triangle. Okay, this is only for right triangles. Then you're going to form 3 similar triangles. And this is how you set them up so that their corresponding angles are in corresponding positions. And then you're able to write a similarity statement really easily after you've done that. I find this to be quite confusing. So I always redraw it, and I'm going to ask you guys to redraw it this year. All right, so let's do the exact same thing here. We're going to identify the similar triangles in the diagram. Okay, so notice you have the big triangle. then you have the second triangle and the third triangle that have been formed. Now I'm going to do the exact same thing that I did up here. We don't have to use colors unless you find colors to be really helpful for you. Okay, but I'm going to start by taking the big triangle and I'm going to draw it, and I like to put my right angle in the bottom left-hand corner. You can put it in the bottom right-hand corner. You can put it wherever you want. It just has to be the same for all three triangles. Okay, so here's my right angle, which is Q. And then I'll just rotate it so that P ends up at the top. So now P is congruent to that one, and M is congruent to this one. So that's my first triangle. Now let me go ahead and do my second triangle. It doesn't matter which order you do them in. Now my right angle is N, right? So this is going to be N. And I want P to be in the same position because P is part of that triangle. So P is going to go up here. And then Q is the last angle in this triangle. So that was triangle 2. And then we'll do the last one. So again, I'm going to start with my right angle down at the bottom. And again, this one's going to have a right angle of N. Now for this one, it doesn't have a P, but it does have an M. And M should be in the bottom right-hand corner. So I'm going to put M down here. And so the only angle that's left is Q. So Q then corresponds with P. So I've used my congruent angles to help me set these up. And so then I can write a triangle similarity statement. Let's just go ahead and do that, even though it doesn't. Oh, no, it does. It says to identify, so we have to write it. So we've got triangle PQM will be similar to, and I'm just going to do the exact same thing. I'm going to start at the top and go counterclockwise. P and Q, right? So N and Q are my right angles. And then M and Q then will also be corresponding. Those will end up being congruent. And then the last one is triangle. Why do I keep forgetting my triangle symbols? I'm sorry. Triangle PNQ. Similar. I almost put congruent. Similar to triangle QNM. And now I'm able, this is really my answer right here. I'm able to identify them, which triangles are similar to which ones, and I'm able to put them in the proper order so that corresponding parts are in the same position. Okay, moving on to example 2. So now we're just applying this to a rooftop, I think. So a roof has a cross section that is a right triangle, as you can see here. The diagram shows the approximate dimensions of this cross section and find the height of the roof. Oh, that's all we have to do, just find the height. Okay, so we're going to set up similar triangles, and then that will help us figure out the height. So I'm going to do the exact same thing. I'm going to draw out my original triangle. Maybe I won't be so perfect this time. I won't use a ruler. How about that? So my original triangle here was, let's see, I'm going to put my right angle in the bottom left-hand corner because that's how I like to do it. We'll rotate it so that T goes up at the top and R goes here. Okay, so I got T congruent to T, R congruent to R. Now I have two other triangles here. So here's the second one, and there's my third one. Let me put some measurements here. So RT is 65 feet. SR is 25 feet. And TS is 60 feet. We're going to need that because we're going to end up having to solve for this height here. And we're going to need to probably set up proportions because we're going to have similar triangles. All right, let me do another one. So we'll do triangle 2. So this time my right angle is W. And it has in common the T with the big triangle is in common. So we'll put those in the same position. And then the last angle that's left is S. Now let's get the measurements of each side. So what is WS? Well, WS appears to be H. That's what we're going to have to solve for. Let's see, we got TS. So TS is 60. And then WT, we're not 100% sure what that is. Okay, so let's see. At this point, we would probably have enough information to go ahead and set this up. And we could then solve for what H is. If not, if we don't have enough information, so I can see that, I've got the hypotenuses, and then I've got one of the bases, I don't have the other base. If I didn't have that, I'd have to do the final triangle. But I think on this one, we're going to be fine just setting up 2 triangles. Sometimes you'll have to go ahead and set up the third one so that way you have enough information. Like, for example, let's say I didn't have this 25 here. Let's say I didn't know that. If I didn't know that and I didn't know this one, well, I wouldn't be able to set up a proportion. Okay, so I think I'm going to go with triangle 2 over the original triangle. So that's how I'm going to set up my ratios. And I'm going to set up a proportion so I can figure out what H is. So triangle 2, let's do, how about we'll go with 60, which is our hypotenuse, over 65, which is the hypotenuse of the other one. So then I'll have H over 25. And then to solve this, because it's a proportion that I set up, so that I would be able to solve, I just cross multiply 60 times 25. Oh, let's see what that is. 1,500. And then I'll divide both sides here by 65. Oops, getting off the screen. So I'm going to have H is approximately 23.077 feet. Please go 3 decimal places unless it says to go to a different decimal place. Okay, so that was using those similar triangles and that right triangle similarity theorem to basically then set up a proportion using corresponding sides to solve for the side that we didn't know. Okay, moving on to our next page. There it is, page 480. Has the geometric mean on it. So, I do encourage you to go into your textbook and read about it, but I'll go ahead and do it for you right now. So the geometric mean, let's go ahead and write this as a sentence. The geometric mean of 2 positive numbers, A and B, is the positive number X that satisfies and it satisfies this. If I put A over X, it'll equal X over B. So the geometric mean then becomes this. If I cross multiply, I get X squared equals AB, right? A times B, I just cross multiplied. And therefore, if I take the square root now of both sides, X will equal the square root of AB. This is all positive. So according to this, because normally if we take the square root, well, that could be like a negative number too. So we could get a positive or a negative. So for this one, we're just going to take the positive. And you're probably saying to yourself, what is Mrs. Frisk talking about? How could you get a positive and a negative number? So for an example of that, let's see. Just do it over here. If I were to tell you that X squared equals 25, Well, what number can I square to get 25? And you're saying to yourself, duh, it's 5. X equals 5, of course. Because if I square 5, I get 25, right? Okay, so that's one of them. There's another number, though, that I can square and get 25. So the other number here would be -5. Right? Because if I take -5, the whole number, and I square it, don't I also get 25? So really, when we solve something like this, it should look like x equals positive or negative, square root of 25, or just 5. I'll just put 5 because I'm running out of room. However, according to the geometric mean, we're only going to take the positive numbers. Okay, so you're not going to get any negatives. All right, so let's find the geometric mean of 8 and 10. All right, so this is really easy. You basically set it up just like this. 8 goes in the numerator of the first ratio in the proportion, and 10, my b, will go in the denominator of the second ratio in the proportion. And then the unknown goes here. So it goes like in the middle. And then when you cross multiply, you would get x squared equals 80. And of course, that would not be an appropriate way to leave this, so we're going to simplify it all the way, okay? So 80, let's see, so if I square root both sides, this becomes a square root of 80. So let's talk about factors of 80. I'll make a factor tree over here. Factors of 80, maybe you say to yourself 4, because I always try and look for like the perfect square factors. So like 8 and 10, not really perfect squares. You could definitely do 8 and 10. But I always try and look for some perfect square factors, like 4. But then I'm still left with 20, which isn't a perfect square, so I'll factor that to 4 and 5. So you can see I've got the square root of 4 times the square root of 4 times the square root of 5. So really, I'll come over here. X is equal to the square root of 4, square root of 4, square root of 5. And maybe some of you guys are like, Miss Frisk, 80 is really 16 times 5, right? That's what this is right here. Okay, so simplifying this even further, the square root of 4 is 2, square root of 4 is 2, root 5. Or in other words, I'm just going to write it over here, 4 root 5. Okay, so now we're going to go with the geometric mean altitude theorem and the geometric mean leg theorem. So they're different. One has to do with the leg and one has to do with the altitude. So I'm going to highlight those ones. So this is my altitude one. And this will be my leg one. Okay, so I'll write them down and then I'll do one at a time, but I'll write this one down and then I'll draw a picture and try and explain to you what I'm talking about. So, let's see. Draw a little divider here. Okay. The length of the altitude in a right triangle is the geometric mean which means in order to find that length, you'd set up something that looks very similar to this. Of the lengths of the two segments of the hypotenuse. Okay, what the heck do I mean? So I'm going to draw myself a right triangle. I'm going to draw it with the hypotenuse horizontal, similar to like what we did in the very beginning. We're going to pretend like this is a perfect right triangle. And the way that we pretend it is we just draw in a right triangle. Look at that. Oh, it's so perfect. Okay, I'm going to label my vertices. We'll go A, B, and C. And I'm going to draw my altitude. And I'll label that with a lowercase a. And I know it's my altitude because it forms a right angle with the line, the base in this case. The hypotenuse is the base, right? So the altitude is forming a right angle with the side opposite it, making it an altitude. Okay, so my altitude is this yellow. I'm going to highlight it in yellow so that it matches altitude. Now, what I've done is I've taken, by drawing that altitude, I've taken my hypotenuse and I've split it into two separate pieces, right? So I've split it into these two pieces, x and y. So what this is saying then, the geometric mean altitude theorem, is that you could find, if you didn't know, for example, the altitude, but you knew these two pieces, then you could easily find the altitude by setting up a proportion as a geometric mean. So it says the length of an altitude in a right triangle is the geometric mean, which means it's in between the x and the y. So the x is the number that we would know, and the y is the other number that we would know. So it's like the a and the b in our definition. And then our altitude is what we wouldn't know. Or maybe vice versa. And so therefore, you would then cross multiply. You're going to get a squared equals x times y. Or in other words, a is equal to the square root of x and y. Positive again. Okay, so that's the geometric mean altitude theorem. There's also one for legs. So the geometric mean leg theorem, which we're going to do in pink, okay, I'll go ahead and I'll write it out and then I'll explain it using a diagram as well. So you're going to do the length of each leg in a right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse adjacent to the leg. Okay, I'm going to draw another picture of this. So another right triangle very similar to that one. We're going to pretend like that's a right triangle, even though it doesn't look like one. Okay, I'm going to label this A, B, and C. I'm going to draw my altitude again, which is going to form a right angle here. Okay, so we have two pieces here. Let's see, I think I'm going to use two different colors. So the length of each leg in a right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse adjacent to the leg. So I'm just going to do one leg in this example. I'm going to do leg CB, okay? So let's call it, what can we call it? How about L? We'll call that leg L. Okay, so we're going to take this leg right here. So each leg. And the segment of the hypotenuse adjacent to the leg. So the segment of the hypotenuse adjacent to the leg is going to be the part of the hypotenuse that has been divided, right? So there's two parts of the hypotenuse. We'll go ahead and we'll call this y again. Okay? That part is adjacent to the leg. So this is the part that I care about. And it's the geometric mean. So the leg that I'm talking about is going to go in the middle. We'll call that L. The leg that I care about, you can name it whatever you want. Okay? And then what we're going to have is we're going to have the entire hypotenuse. So our entire hypotenuse goes up here. Oops, gotta spell it right. So it's the geometric mean with the entire hypotenuse and the segment of the hypotenuse adjacent to the leg. So that's the y. So in this, I'm going to go ahead and write out a description of what I mean by that. So y is the segment of hypotenuse adjacent to leg. Means it touches. Okay, so let's see what I can do here. So I've got, can I use colors? Maybe that's not a good idea. Let me go ahead and write here leg. Okay, so the leg is always the geometric mean, which means it's in between. And you would hopefully be given, the hypotenuse, which is the entire hypotenuse. Like here it would be AB. And then y, or the segment of the hypotenuse that is touching the leg. All right, so let's go ahead and let's do a couple of examples here to maybe drive that home. All right, so first of all, A, find the value of each variable. Well, you can see that this one's an altitude, right? So I have to find the length of the altitude, and I'm given, so that altitude is dividing the hypotenuse, right? Because that was a right angle, so this is my hypotenuse, dividing it into two segments. So should I use the geometric mean altitude theorem or the geometric mean leg theorem? Well, nobody's talking about legs here, right? This is all hypotenuse and altitude. So there's no leg, so we're doing the altitude theorem, the geometric mean altitude theorem, which, once again, let's read that again. The length of the altitude in a right triangle is the geometric mean, right? So it's going to go in between of the lengths of the two segments of the hypotenuse. So the length of the two segments will go over here. Okay, so I'm going to set up a proportion. The altitude is that geometric mean, so it goes like in the middle. Oh, we'll use X, not A, because they give us that. And it doesn't matter where you put these two, so I'll just put 10 and 4, because when you cross multiply, it doesn't matter the order, right? If I put the 4 here, the 10 there, it doesn't matter. You're going to get the same exact number. So I get x squared equals 40. Simplifying that, well, this is 4 and 10, right? So I really get x equals the square root of 4 times the square root of 10. 10, there's no perfect squares in, so just simplify that. X equals 2 root 10. Okay, next one, I have to find y. Well, y is a leg, right? Y is a leg. And there has been an altitude drawn, but nobody cares about the altitude. There's not a number on it. I'm not looking for it. However, once again, the altitude has split my hypotenuse into two different segments, of which I know the actual values of, the lengths. So I'm going to end up using the geometric mean leg theorem, which says the length of each leg in a right triangle is the geometric mean. So when I set up my proportion, the leg is the geometric mean. So it goes in the middle. It goes in the bottom of the first ratio, top of the second ratio. Of the length of the hypotenuse and the segment of the hypotenuse, of the length, not length, there's only one length. Of the length, we need to fix that. the length of the hypotenuse and the segment of the hypotenuse adjacent to the leg. So the full length of my hypotenuse here is 11. So that's going to go on one of my ratios. And then down here, I need the length of the segment that is adjacent to the leg. The length of the segment of the hypotenuse that's adjacent to the leg. So which one's it going to be? Which one's adjacent to the leg that I care about, this y? Is it 3 or is it 8? It's 3 because that segment is touching this leg. So it might be helpful if I don't know, I could do the color. So there's the segment of the hypotenuse. And here's the leg. You can see how they're touching. If I chose this segment or part of the hypotenuse, it would not be touching my leg. So I'm going to choose the 3. So I get y squared equals 33. Well, 33 is a prime number. I lied. It's 11 and 3. But 11 and 3 cannot be broken down. Those are both prime numbers. That's what I meant. So this is just going to be the square root of 33. You have very little space for a summary here, so you might want to do it on a separate sheet of paper, because I think you have the notes I gave you or that you are copying or is just one single sheet of paper. So you can just do the summary on your notebook paper.